Hello everyone. Thank you very much for checking this video out. I'm a professor in the Department of Mechanical Engineering at Virginia Tech. The purpose of this video clip is to explore the role of chemistry in fluid dynamics. So fluid dynamics is a discipline that studies the motion of fluids as well as the interaction of the fluid flow with the surrounding. Fluid dynamics is everywhere in our life, and in fact, for example, hurricane is basically a classical fluid dynamics problem. And if you threw an olive into a cup of cocktail, then you see this beautiful splash, and that is also a classical fluid dynamics problem. And even if we just breathe, then we actually inject a jet into the surrounding air, and that is another classical problem in fluid dynamics. So fluid dynamics can be very useful. For example, design engineers can study the airflow near a speeding car, and that can help us to decrease the drag experienced by the race car, and hence we can make it go even faster. And fluid dynamics can be just also purely fun. For example, we could study the air flows near a running dinosaur and envision how much drag this monster actually could experience at the top speed. And if we have a cup of afternoon tea, we could also wonder what would the flow near a slice of cake if we have a gentle breeze brushing our cake. So by and large, fluid dynamics has been studied and practiced for thousands of years. And most of the time, we focus on microscopic behavior. And it's fair to say that the classic fluid dynamics say neither individual molecules or their interactions. And this can be appreciated by looking at the governing equation of fluid flow, which is the Navier-Stokes equation. So here we show a Navier-Stokes equation for a classic Newtonian fluid. And on the left-hand side, we see the mass time acceleration term. And on the right-hand side, we see the various forces responsible for driving a flow. So now the key thing that you can observe from this equation is that the nature of the fluid actually are entirely encapsulated in two numbers. One is density and the second is viscosity. So here we really don't see any individual molecules as well as interactions between these molecules. They are all hidden, packed, or encapsulated in these two very simple numbers. This is in sharp contrast to chemistry. So in chemistry, most of the time or a lot of times, we are very interested in molecules, right? So how atoms are bonded to each other and how, if we have one molecule here, say, for example, a lithium ion that is chelated by a very complicated molecule like this, right? So how their electron cloud actually will interact. So hence, really one key element or key aspect of chemistry that we really oftentimes are looking at individual molecules, their bonding, their interactions, and we care about specificity. And that is, if we have molecule A and we have molecule B, the shape and the size and how atoms are arranged make a great deal. And chemists are very obsessed in studying this kind of thing. And this is actually can also be appreciated by looking at the fundamental equation in chemistry, and that is the Schrödinger equation. So in this equation, both the wave function as well as the Hamiltonian are mostly, right, so people solve them or define them, explore them at a subatomic scale, right? And so here, really, the focus is a lot of time. It's at the kind of the atomic level, right? So here, things are very much oriented towards single molecules, or a lot of time. So now we say that on one side we have fluid dynamics where we really don't see individual molecules or we don't care about their interactions as long as we get our density or viscosity correct. Well, on the other side, we have chemistry that is relentlessly focusing on molecules and even smaller electrons. So it's fair to say that fluid dynamics has been largely separated from chemistry in the past. So this actually have served us very well. For example, a design engineer, when he try to optimize the flow near a race car so that we can reduce the drag, right? He does not have to, he or she does not have to worry about the size and shape of the oxygen and the nitrogen molecule, and even less so about, say, for example, the vibration of the atomic bonds. So, however, in the past decade or so, a lot of progress has been made in engineering practice that has significantly pushed the envelope of fluid dynamics. And this actually has forced us to take a look at the traditional paradigm where fluid dynamics is segregated from the chemistry. So in a series of videos, we would like to explore the role of chemistry in fluid dynamics. In this video, we explore the importance of chemistry in water ethanol separation. In many biochemical as well as agriculture technologies, fermentation will produce valuable ethanol that can be used for lots of different purposes, like beer, for example. So now in generating ethanol, however, water is also inevitably generated, and to separate the valuable ethanol from water, so there are many techniques possible. For example, you could use distillation, as simple as that. However, this kind of technologies are usually expensive because it involves phase change. One of the least energy-intensive approach is so-called membrane separation. Basically, you run the mixture through a membrane separator, and only one type of molecule, say ethanol or water, goes through, and this you achieve a separation. Designing a membrane for achieving such a separation, however, is a pretty non-trivial business because the materials that are being separated here, and water and ethanol, are chemically quite alike. In fact, they are completely miscible. So here, what we would wanted to say is that the development of the materials really have to make a lot of progress that holds some promise of addressing this challenge. In particular, graphene is emerging as a promising solution for serving as a separation membrane. Graphene is essentially a single atomic layer thick carbon sheet, as we show here. So now if we can knock holes on this carbon sheet, then we can potentially end up with a membrane. So the good thing about graphene as a separator is that because it's a single atom thick, so that means that when fluids flow through this, right, it has a smaller resistance, and this implies less energy consumption. However, it turns out that to make a good graphene separation membrane is pretty tricky. And for one, if you make a hole on the membrane, right, so the smaller you make and the more precise you make, the more difficult it becomes. And also, so when designing a graphene membrane, we are also facing a fundamental challenge, and that is this paradox between high flux versus high selectivity. For example, if you make the pool on the graphene membrane too big, then you have a very high flux for given pressure difference, and hence you have very energy efficient membrane. But both water and ethanol go through, and hence you end up with no selectivity, which is not good. So here we saw that it is possible to use chemistry actually to help design a better graphene membrane for separating ethanol and water. So we do so using a computational model. So shown here on the left is the model, the molecular dynamics model that we have prepared. Essentially, we have a graphene membrane sitting here, right? So on top of this is a one-to-one mixture of ethanol and water, and on the bottom is pure water. We apply a pressure on the top piston to mimic what we do in practice, and we watch how much water and ethanol go through this. So now the key part of this obviously is the membrane. So here we propose three possible kind of design. One is we simply dug a hole and functionalized using a carboxyl group. So in this case, each of the carboxyl group is neutral, so we end up with Q equals to 0. Now in the second case, we deprotonize one half of the COOH group, and hence we end up with an electrical charge of -3 electron. And finally, we can also fully deprotonize all the carboxyl group, and hence we end up with a -6 electron. So in all these cases, the nominal diameter of the pool size is 1.12 nanometer. We select this rather large size because remember, the smaller you want to make it, the more difficult, and also the smaller it is, the higher resistance is, then more energy you have to pay. So now let's see how this membrane actually works in our computational model. So shown on the left figure here is the number of water and ethanol molecule passing through this as a function of time. So you can say that as a function of time, this increases rather linearly, and by computing the slope of these curves at larger time scale, we can actually compute the flux, which is shown here. So what we say is that when the edge of the graphene pool is neutral, right? So we have something like here, and so when we increase the charge, right? So what we found is that the flux of water increases, and meanwhile, the flux of ethanol decreases. So what this means is that now we have enhanced selectivity, which is something that is very valuable. In addition, we have a higher flux of water. That means that we can get rid of water in a shorter period of time. So what this tells us is that it's possible by manipulating the chemistry of the edge of the pool through functionalization and deprotonization to actually engineer a pool or a membrane with higher selectivity. And this is one of the fundamental issues that sometimes people have to deal with in fluid dynamics as well. So now the question is how or why this works. Well, to do this, we look at the distribution of water and ethanol inside the pool, inside this one atom height thick pool, right? So with a diameter of 1.12 nanometer. So on the top row are the distribution of water molecule inside the pool, and the yellow means there's more water molecule, and the blue means less water molecule. Shown on the bottom is the ethanol distribution, and here we show the mole fraction, right? So again, the red means that there's a lot of ethanol there, and blue means none. So in general, as we can say, right, so as the charge became more negative, we say that there are more and more hot spots for water molecule to reside, and meanwhile, right, so there are less and less ethanol molecule. So what this tells us is that through functionalization, we actually can change the occupancy of water and ethanol inside the pool, and this directly affects the flux, because for ethanol to pass through this, right, so it first has to get into this pool. So a lower occupancy indicate a smaller flux, to say, right? So now the question, of course, is why this is so? Well, there are two reasons, I think. For one is that when you electrify your pool, right, so now the interaction between the functionalized edge, right, with both water and ethanol became stronger. However, because the water molecule is smaller and is more polar than ethanol, right, so the increase of the interaction actually is stronger. So this is actually clearly shown in the figure here, and that is the radial distribution function of water and ethanol around this functional group. As we can see, when the edge became more highly charged, right, so the water peak actually increased, so there's a lot more water surrounding this carboxyl group, deprotonized carboxyl group, and while at the same time, so the ethanol actually decreases. Okay, so that's just one way, and that is, electrifying this, right? So water became more competitive to access the edge of the pool and thus reside inside the pool. Another reason for this is electrification actually also brings in counter ion, in this case, the sodium ion, into this pool. So now remember, right? So the sodium ion actually became associated with charged site, right? So once they do that, right, so now this ion will reside in the pool. What they do is they will suck in more water molecules, right, because water molecules like the ions, right, so ions are highly charged, right. So this is indeed what we have seen here, right, so with the radial distribution function of water and ethanol around the sodium ion, right. So at the same time, because the water molecule get in here quite easily, right, much easier than ethanol molecule. So essentially, they kind of outcompete ethanol molecule in terms of accessing this sodium ion shown here, right? So what this means is that the pool effectively became smaller to ethanol, right? So, but it's actually still as wide to water molecule. This also helps to bring in more water molecule and remove ethanol, which together, right? So now that you have less ethanol, right? So then the ethanol flux became smaller. So as we can see from here, right? So by leveraging chemistry, actually it is entirely possible for us to engineer better materials to achieve a problem that typically are a lot of time targeted using fluid mechanics principles. So if you are interested in more technical details, for example, the quantitative analysis that we sketched out here, you are welcome to read this paper, which was published in 2018 in the Journal of Carbon. With this, I would like to conclude. Thank you very much.